So remember from yesterday, we were working with the J omega compact scalar. And we had this Donaldson-Fujiki construction. So there's the first part to this is what we discussed yesterday, is that if you have the group G of exact omega, or maybe let me call this omega naught, symplectomorphisms, and this is going to act on this infinite dimensional manifold of compatible complex, almost complex structures. By pullback, and that this action is this comes with a kind of formally Kähler structure, and the action is Hamiltonian. All the Hamiltonians for infinitesimal generators of the action fit together into a moment map. And we call it M. So this is going from J to the Lie algebra, or the dual of the Lie algebra of G, which we identify with the Lie algebra using this L2 inner product. So this is mapping to C infinity zero average on M. And so if you fix a J, which is actually inside the integrable locus, and this is mapping to the usual, say, Riemannian scalar curvature. Sometimes maybe yesterday I just wrote S. Maybe I should just call it scal, so it's clearer. So the scalar curvature of the Riemannian metric, which you get if you combine J and omega, minus its average with respect to omega naught, which is fixed. Now, of course, you can choose this constant as you like, but this is the only constant for which the zero locus of the moment map is potentially non-empty. If you integrate, you see that. But this is only the first part. So that just says that if you remember solving this, the equation that the scalar curvature is constant was important from the point of view of moduli spaces we had yesterday. And this is telling you that if you try to do that, you're actually trying to solve a zero moment map problem, which is interesting. But there's a second crucial part to this Donaldson-Fujiki construction, which is complexification. So this means that so even if we cannot define the complexification of this kind of, this is G is a real infinite dimensional Lie group, and you might wonder, does it have a complexification? That's not well defined. Still, the orbits of some sort of GC action on J are well defined. So how does it work? So if you think you have, well, first of all, you fix some exact symplectomorphism. So if you have, so right, let's so what is a tangent space to the orbit through some j, this orbit O. Let me write O for g times j, its orbit. So this is just given by the first order variation of f star j along the action of g. So this will be just the derivative of j in the direction of the Hamiltonian vector field corresponding to phi, well, f star j. And this is as phi varies inside the Lie algebra of the group. So there's a well-defined infinite dimension, of course, tangent space to the orbit of the G group action at a point. And you can, so this gives you a distribution inside the tangent bundle of this big space J, and you can complexify this distribution. So there is a complexified distribution, which is just, let me call it D maybe, and it's the leaf of this distribution at this point f star j. You know, it's just what you would expect. You get the tangent space to the G orbit, and then plus. Remember, you have this tautological, almost complex structure, which is acting on the tangent bundle to this J. So if I want to complexify, that's the only sensible thing to do, acting on the real part with this J and adding up. So now the second main point of this construction is that this proposition, this V distribution D is formally integrable. I just mean it's involutive. Which in infinite dimension does not mean it's actually integrable, but in fact, in many cases, you can actually find integral leaves for this distribution. So just to make my life simpler, now, and I think in many places in what follows, I just assume that we are in the projective case, when the polarization that we fix is actually algebraic. It's a Festian class of some positive line bundle. But this is not necessary. I mean, it's just to make my life easier. And then in this case, you can actually write down integral leaves. So we can describe integral submanifolds of this formally integrable D as follows. So how does it work? So I have a space, I want to start with the space, say F, which is given by pairs of some omega, which is a Kähler form lying in the Kähler class of omega naught. So some other Kähler representative of the same Kähler class. The second element in the pair is some diffeomorphism F, which lies in the connected component of the identity inside the group of diffeomorphisms of M with a fixed lift to the line bundle. So you have pairs like this, And then they need to be such that this second component, this diffeomorphism, must be such that it pulls omega back to omega naught. Now, this is a special case of Moser's theorem. If you have some other omega inside the same Kähler class, you can always pull it back to omega naught with some diffeomorphism. And we insist that the diffeomorphism is in this class here. And then you have some tautological, or I should say some evaluation map. And let me call it maybe big phi, which goes from this space of pairs here, which you can think of as some infinite dimensional manifold 2. This is mapped into the space of almost complex structures. And this is sending some j to its, this is sending for fixed for a fixed j here. So I send a pair omega f. This is sent to the pullback of j. And the second proposition, that this is in fact an integral submanifold through j. The image, so phi, the image of this evaluation map from the space of pairs is in fact an integral submanifold of this distribution, this complexified distribution through j. Okay. And finally, this is already quite interesting. So it means that you can certainly complexify the Lie algebra of the group G. It's not at all clear that you can find an actual infinite dimensional complex Lie group that has the Lie algebra. And I think, in fact, there's a theorem that tells you that you cannot, that there's no such thing. But still, even if this group does not really exist, the orbits of its wannabe action on this space do exist, and they are very nice somehow. So we are morally in the situation of some kind of infinite dimensional angle of a reductive group acting on a space J. So morally, we have GC acting on J. Well, we only have the orbits, but it's good enough for us. And finally, you combine this with an elementary observation. And the last step in this construction for now is that, suppose we're interested in the scalar curvature, remember, of matrix, which are obtained by fixing some reference symplectic form and then moving around complex structures. And suppose I move them around by acting with some element f, say, which is in this group. So if I'm interested in understanding the scalar curvature, solving for it to be constant, and I wonder what happens if I move along these complexified orbits. And then it's not hard to see that this is just the same as the following. So in particular, if you want to solve, you want to try to find some element in the this kind of this complexification of G that takes you to something that has a constant scalar curvature. So you want to move inside a GC orbit so that you hit a solution to your zero moment map. Well, that's this simple fact tells you that it's the same to actually fix the complex structure and try to move inside the Kähler class alternatively. So, the slogan is that solving Sj to be the only possible constant inside a GC orbit which is somehow one version of this problem is equivalent to solving that S omega should be constant for omega inside this fixed Kähler class. And this is much more manageable from the analytic point of view because we have tools like, well, for start, we have something called the Didi-Bar lemma, and we can make progress on this. This is somehow having your J as a variable in a PDE is much more complicated. But this is the problem that relates, at least morally, to GIT, right? So we've heard in the last lecture that there is this very important theorem called the Kempf-Ness theorem that says if you want to find that zero of your moment map inside the orbit of your complexified group, then you're going to be able to find such a zero if and only if the orbit is polystable. And so this is morally very, very close to this Kempf-Ness type situation. And this Larsson-Fujiki construction says that, okay, that's this kind of GIT problem is in fact, you can interpret it as trying to find some Kähler metric in a fixed class for which the curvature is constant. This is Cal, if I forget about it. So this whole package is important to actually prove theorems, but it's also very important for motivation. So the first thing I want to say is that this motivates a definition of K-stability. And this is actually what happened historically is that, you notice that you have this GC action on J, and you want to try to make sense of the Hilbert-Manford criterion for this GC action, rather for the orbits of this GC action. So you want to understand if there is some kind of infinite dimensional version of a Hilbert-Manford criterion which applies, and which, if it tests positive, then it tells you that you can find the zero of the moment map in the, yes, please.
I may have missed something, but implicit in your slogan, is it true that two homologous Kähler forms or symplectic forms differ by a diffeomorphism?
Yeah, I said, I think at some point that I'm using Moser's trick.
That's Moser's trick.
Moser's trick, yes.
And that's global, that's not just an infinitesimal state.
No, it's global because M is compact.
Sorry,
I'm using compactness too. Yes. Okay, so what would that be? Well, it's not too hard to guess. I mean, you have a first guess of what a one-parameter subgroup could look like. So, first guess for 1PS would be just together with its limit point, remember from JT, you want to have 1PS, take its limit point and compute the Hilbert-Mumford weight there. So your first guess would be that since we're working with a complex structure on a fixed manifold, you want to have a family. You want to have a C star equivariant family, say, let me call it maybe curly X to C. So this C star acts on the base and it leads to the whole space. Maybe such that the central fiber X naught is in fact M naught, yet another compact complex manifold. So this is some kind of dream case in which the 1PS actually stays inside the space J, and the limit point is some other complex structure, possibly different on the same underlying C-infinity manifold. And then if you're in this ideal case, then you immediately have, you know what the Hilbert-Mumford weight should be, because if you look at the proof of the Kempf-Ness theorem, it tells you that HM weight is just a moment map evaluated at a specific point. So this is telling us that it's giving a good guess of what the Hilbert-Mumford weight should be. So in this case, if your 1PS is like that, the limit point is M naught, but it comes, since the family is C-star equivalent, since it comes from a one-parameter subgroup, it comes also with an action of C-star. This C-star actually corresponds to some, so you have this C-star inside M, acting on M naught, is generated by some vector field, say X, which is inside the group of Hamiltonian automorphisms of this special point, M naught, which is the intersection of G with the automorphisms of M naught, J naught. So it's biomorphisms of M naught into itself, which are exact also as symplectomorphisms of, which are also exact symplectomorphisms of omega naught. So this is Hamiltonian in particular, and so the Hilbert-Mumford weight for this 1PS, and it can only be this pairing between the Hamiltonian phi, which generates phi is the Hamiltonian of this X. So I said that if you look at the Kempf-Ness theorem, you realize that the Hilbert-Mumford weight is just the moment map evaluated at the special point. So it's the pairing on M between this M naught between phi and the scalar curvature. So there's no freedom. This is the only thing that it could possibly be from finite dimensional GIT, if you want anything like that to be true. And this is this is the correct interpretation for something that had been known for a long time, which is called the Futaki invariant. So this is a Futaki invariant. So this Futaki observed that this quantity is extremely relevant to this constant scalar curvature problem well before the moment map interpretation. And I don't know how he did it. Somehow he just guessed that it's the right thing to do. But a posteriori, it's just the Hilbert-Mumford weight. So it's fantastic. The problem with this is that it's way too naive, because you cannot really expect that it's enough to test for things which are actually smooth one-parameter families, like one-parameter families for which this map here is smooth. All the fibers are complex manifolds. That's way too much to expect, right? You expect that you also need to allow for some singularities to happen at the special point. And this is because this space J that we are working with is, you need to complete, it's not complete. You need to somehow complete it at infinity. You need to allow some limiting points. And so you need a better version, a more intelligent version of this Hilbert-Manfred criterion, for which the central fiber of the 1PS can be singular. And so there are proposals. So one proposal is this original version of K-stability. Proposal for actual 1PS that you need to test for. These are what are called test configurations in this area, but in reality they are just a certain kind of one-parameter degenerations. So you need to have a family, just in a nutshell, over C, which is now a flat family onto C. You also realize with examples that you need to impose some regularity on the total space, and one way to do it is to say that it's normal. And remember to make my life easier, I said I would mostly work in the projective case, so let's do it here too, but it's not necessary. You can do it more generally for Kähler and a purely Kähler situation. So you also want to have some relatively ample line bundle. And all this is C star equivariant. And it's such that a generic fiber is just your manifold. So it's enough to ask, because we have the C star action, that maybe the fiber over the point 1 inside C is just M omega. Right, it's M L. Well, L is the line bundle whose first chain class gives you the polarization omega. Okay, and this is allowing singularities, which we need to do. And then the other thing we need to do is that, this is the, sorry, where is the, the Hilbert-Manfred weight is up there. And you see, if you have one of these more promising one-parameter subgroups, this quantity here now looks pretty suspicious, right? Because how are you going to compute this thing on a very singular space? It's you will need to make sense of the scalar curvature on a possibly rather singular central fiber. So that's you can do it. You can do it in some cases, but it's not clear how general you can do it. So it would be much better to replace that with a purely algebrogeometric quantity, which agrees with that whenever you can compute that differential geometrically, but which clearly makes sense algebrogeometrically, and it's possible. There are many ways to present it, but let me give you a quick way to write it down. What is this new Hilbert-Manfred way? The Hilbert-Manfred weight you can obtain by this trick. This is worked out by, there were various people working on this, and this way of presenting the Hilbert-Manfred weight is due to Wang and Odaka, is that you first compactify. You have this canonical compactification. Let me call it x bar over P1, which you can do it because you have the C-star action. So you compactify by gluing in with the trivial family at infinity using the C-star action for the gluing. Over, say, C inside this P1. And then once you have this compactification, you can compute intersection numbers. This is it's a normal variety. So the following quantity is well defined. It's a constant which I'll explain in a second times a bunch of intersection numbers. And mu is the following constant, which can be computed on the generic fiber. So it's just C1m dotted with Li minus 1 divided by the slope. Okay, so this is, it's not obvious at all, but it specializes to this quantity whenever you can actually compute it by some computation. And but it's defined much more generally for this more promising class of one-parameter subgroups. There are other ways to present it without doing the compactification first, but they are more complicated. Please.
So the equation in the middle board, do you take this to be a definition of the Hilbert formula in this context? Or
Yeah, it's a definition. It's the only way.
Sort of independent definition of the left-hand side.
Which this you mean this one?
No, sorry, the Hilbert.
No, this is yeah, it's this is the Hilbert-Mumford way. It's the way you would define it in GIT by saying it's given by flowing along the 1PS to a fixed point and computing the moment map there for this induced action you have on the fixed point, and it's the only possible way to do it. It would be great if it's enough to to just test for this.
But so what you have there is all depends on the central fiber, but this depends on the whole generation, right?
Yeah, as I was saying, there are other ways that don't use this compactification. So it's you can. This is a way to compute it if you like. There are alternative definitions that make it manifest that it does not depend really on the total space, but. I mean, it can be computed purely on the central fiber. That's what I want to say. Yeah, it's possible to do that. Just compute on the central fiber, forgetting the rest. But you need this induced action. But this is somehow the neatest way to present it. It's the most compact way going through this canonical compactification. Okay, then. I hope this more or less motivates. I mean, we didn't have that much freedom in retrospective. We used the finite dimensional GIT as motivation. This was the only possible quantity which was forced on us. And then some clever people realized that it can be computed algebra geometrically in many ways. This is one way, which is compact to present. So the actual question is this going to work? So is this actually enough to test for? So you might formulate a conjecture, which is usually called the Yau-Tian-Donaldson conjecture.
Excuse me.
Please.
So if the test configuration is smooth, then both quantities agree.
The central fiber needs to be smooth, not the total space, because this is compute. No, yeah, if the map pi is smooth, then
Both
they agree. Yes, that's true.
But that has the advantage that works for us.
And this one you can compute whenever total space is just normal. The fiber can be whatever you get as a fiber over 0 in this situation. So the conjecture would be that Youtian Donaldson would be that S omega equal S is solvable so that you can find a 0 of the moment map in your GC orbit if this df, the Silberman weight is always non-negative, and it's 0 only if XL is, well, only if, say, the central fiber is actually isomorphic to M. So that the 1PS corresponds to some family which is trivial as a family of complex manifold, but it comes with a non-trivial vector, holomorphic vector field. And so this would be precisely polystability. In the GAT sense, so that the Hilberman weight is always non-negative and 0 only for things that come from the stabilizer of the point. So we don't know if this is the right conjecture yet, but of course there are some great results. So maybe the main thing is the theorem by Chen, Donaldson, and Soon. The conjecture is true when the polarization is the anti-canonical. Which is the Fano case. And now it's also known much more, in many other cases allowing singularities or allowing some boundary and so on. But this is the crucial result. Well, apart from that, yeah, we don't know yet. And actually, many people think that this is, you need to have a stronger version of a stronger stability criterion. This is not enough away from the Fano case. Okay, so now I wanted to talk about some other applications of this Donaldson-Fujiki construction in two directions. So one of them is the deformation theory of such special manifolds of constant scalar curvature. So these are, I'm going to talk about things that come out, flow out of this moment map picture, but they are highly non-trivial theorems in their own right. So I'm not saying that they are just application, not just silly applications, that they are deep theorems. Of constant scalar curvature manifolds. So the situation is that, suppose you have M J omega, or let's do it in the projected case for simplicity, but it's not necessary. and suppose that it's one of these special, well, it's one of these good stable manifolds for which you can solve the equation. The curvature is constant. And now you wonder about the formation of complex structures. Can I deform the complex structure while preserving this stability property that scalar curvature is constant? And so let me tell you morally what is the result and then the precise statement. So remember you have this group K, which is the intersection of exact symplectomorphisms of some underlying fixed symplectic form in this class with the automorphisms of Mj as a complex manifold. These are called Hamiltonian automorphisms. And it's actually possible to show that this K is a compact group because it's an isometry group of some Riemannian matrix. So by some general result, it's compact. So you have attached to this situation, you have a complexification, Kc. You have a reductive group, Kc. And by a theorem, which is due to Matsushiba, this is not just any group, it's actually the group of automorphisms of M as a complex manifold that lift to L, and you fix a lift to L. So this shows that for this class of manifolds which are stable, the automorphism group, this automorphism group is actually reductive, which is not true in general. If you have a complex if you have projective manifold, the group of automorphisms of this as a projective manifold is not reductive in general. Just think of P2 blown up in 1 or 2 points. But it's true if the manifold is stable in this sense. So now you have a very good candidate, right? Because you have this group Kc, which is reductive. And by this characterization, so it's going to act on some H1 tilde. How did I call it? Yeah, which is acting on some space of first-order deformation, so which is like sitting in H1 of the holomorphic bundle, so the space of first-order deformations. There are those preserving L. And so the expectation you have is that because everything is now like first order, you could expect that finite dimensional GIT stability with respect to this action of a reductive group is very important to understand the deformation theory, and that's actually the case. So I realize that time is kind of short. So maybe let me just have this slightly vague formulation of this theorem of Szekelydi and Brande that says that the directions, the deformations for which S omega, say J prime, G omega naught J prime. That's small polarized deformation J prime for which this is still solvable. The equation is still solvable in the slightly perturbed complex structure. Correspond precisely to the polystable orbits, the Kc of this action of a finite dimensional reductive group on a finite dimensional vector space. And in fact, you can use this so you can promote this to a corollary that says that so you have these small deformations M prime L prime of ML are still in this good class of CSCK, for which the equation is solvable, if and only if they are actually K polystable. So the conjecture is true at the infinitesimal level, and the proof of this fact uses very heavily this moment map picture, but does not follow easily from the moment map picture. And there's a second kind of confirmation of this conjecture, which is still a kind of deformation, but in a different sense. Let me try to explain. So there is a class of theorems known as Arezzo-Packard type theorems, which have actually contributions from many people. I should say Arezzo-Packard, Singer, and Sakaidi theorems. But I want to give you one statement which is kind of a special case, but still quite general. Now suppose you have, just as before, you have M omega J, which is one of these good stable manifolds to start with, CSCK. So you can solve that. Let's fix that omega is actually a solution, so the scalar curvature is actually constant. Now let's choose points, P1 up to Pm inside M. And let's fix a moment map. Let's call it mu from M to the dual of the Lie algebra. K. This K is the Lie algebra of this real group K, the group of Hamiltonian automorphisms. Then if the sum from I equals from up to M of moment map values at the point Pi is just vanishing, so the sum of so that the configuration of points is kind of balanced in the sense that if you add up all values of the moment maps at the points you chose, you get 0 inside the K dual. And say for simplicity, let's suppose that you've blown up enough points so that the automorphism group of the blow up is just the identity. Then this other manifold, this kind of small perturbation of M. Is still CSCK. For epsilon lying in some small interval. So you can, rather than deforming, you can try to somehow perturb your manifold more radically by blowing up points, for example. You pull back the class from downstairs, it's no longer positive, it's semi-positive, but if you perturb it a bit in the direction of the exceptional divisors, this is now a Kähler class, well known. And you might wonder, okay, if I stay close enough metrically so that this is epsilon close to 0, is it still CSCK? And the result is that in general it's not. There is an obstruction. The obstruction is precisely coming from a moment map for the action on the original manifold, so that this configuration of points should be balanced in that sense. And similarly to what we had for deformations before, you can promote this to K-stability in one special case that's not as general as we had before. This is a theorem of Zekahidi. It says that the situation above, we have the blow up at a single point with its polarization is CSCK for very small epsilon, if and only if it's K polystable. The second theorem. So the conjecture is also true in this other perturbative situation. When you blow up a single point and stay close metrically to the base manifold, then it's precisely polystability that tells you when you can find the zero of the moment map in the orbit.
You don't assume there that the automorphism is fine.
No, now it's the automorphism group is you mean upstairs in the blow up?
No, in this theorem of Gauss.
No, but also before it, the automorphism group on the base is just anything. I'm saying that I'm blowing up so much that I don't have residual vector
Yes,
fields.
you blow up many points.
Yeah. Just to make my life simpler. There are.
You blow up one, I know it's not true.
It's if you blow up one, it might be true that you don't have vector fields anymore, or it might also not be true. But the theorem still holds. It's this generality. Okay, so these two theorems, in the last maybe 2 or 3 minutes, I wanted to show you an example where they come together more or less naturally. You can ask yourself if there is some natural problem to which these general results of Zekahidi, Brunle, Arezzo, Packard, and so on, they would apply. So they would say something interesting in the example. And so I want just to very briefly mention some example, which is from some work in progress. Which is an application to something called Landau-Ginzburg models. And so precisely the situation is that if you have the context is that of the mirror symmetry theory for Fanos. But maybe let's specialize immediately to Del Pezzo. And then if you have a del pezzo, say S, this general theory posits that there should be some mirror to this del pezzo surface, which is not just a variety, it's a variety together with a map down to C, which is called the mirror LG model. Whatever it is so it's a very famous theorem, of course, you might have seen in many talks. So what happens is that, roughly speaking, the complex and so the Kähler moduli and complex moduli should be exchanged between the two sides of this picture. But for the example I have in mind, all we want to do is notice that this is non-compact, must be non-compact. Why? Because this is a non-constant map to C. And so if you want to somehow construct moduli on this side of LG models and somehow try to match them to moduli on the del pezzos, or Fano in general case, it's a good idea to try and compactify. And people have done that in rather large generality. So it's good to fix compactification. This was first pointed out by Katsarkov, Kontsevich, and Pantev, and they use that compactification to prove results about the local moduli of such LG models. So now, for the sake of this simple example, the slogan is that what we need to do is to take one of these, I think the correct words to say are Calabi-Yau compactification of a toric LG model. Calabi-Yau means not that the total space is Calabi-Yau, but that you compactify this to a fibration, say, from W bar over P1, so that the general fiber is, in this case, an elliptic curve. And if you add log to this, people mean that the fiber at infinity is actually an anticanonical divisor on this compactification. Okay, so let me just give you the example. Since people know how to do it for del pezzos for sure, also for Fano trifolds, I think the construction is more or less complete. And for example, if you start from the cubic surface, then the compactification is described quite easily as follows. So you start from S3, a smooth cubic surface. There are several different toric Landau-Ginzburg models, each with their own compactification. There is one which looks like this, it's just P2. This is the other side. The construction of a compactified mirror is that you need to take P2 with this triangle of lines, and then you need to, in this special case, when there are no singularities, you don't need to resolve anything. But you need to resolve the base locus of some anticanonical pencil on this. So it will be given by a cycle of length 9, so which is away from the torus fixed point of a toric structure on P2. And this is the base point of an anticanonical pencil. So the BS of some pencil. So the question is, if for these compactified mirrors, you would expect that the complex moduli, at least, so that the map that takes you to the mirror should land inside this inside some Hausdorff moduli space, because the complex parameters on this mirror correspond to the Kähler parameters on the other side. So just a bunch of coordinates in a vector space, which is certainly giving you something Hausdorff. So the question is, can you make this compactification land into some Hausdorff moduli space of surfaces, which in this case will be rational elliptic surfaces. So this W bar in this case. For all the Petzos, it's a rational elliptic surface. And the answer in this case is yes. And also, work in progress, it can be shown in many other cases. It's just an example. And one way to do it is to use this deformation theory plus blowing up, because that's what you need to do, blow up these points to land inside some space of K-stable rational elliptic surfaces. You need to check that this configuration you blow up is balanced under the action of the automorphism group. The deformation theory comes in because the points can collide, they can come together, and you need it at that point. For example, the anti-canonical class goes to something which is just 3 points. This is the most interesting and most singular situation, and you address it using deformation theory. Okay, maybe I'll stop here. Thanks a lot for your patience.